Hello, and welcome to Graphing Quadratics from Standard Form. All right, so we know from looking at our other quadratic videos that every quadratic has the shape of a parabola. But here's a better fact. We could use the standard form of a quadratic to find all the information we need to graph the corresponding parabola. It doesn't have to be in vertex form. So here's going to be our steps. All right, so first of all, we want to determine if the graph opens up or down. So we'll look at the a value. Next, we'll find the vertex and the axis, the equation of the axis of symmetry by using this little vertex formula, x equals negative b over 2a. Keep in mind that the standard form for a parabola is f of x equals ax squared plus bx plus c. So when I'm referring to a and b, and eventually I'll be referring to c, I'm referring to the coefficients of a quadratic in descending order. So sometimes we might have b as 0, sometimes we might have c as 0, but we'll never have a equal to 0. So we'll determine if the graph opens up or down. We'll find the x-coordinate of the vertex, and this gives us the equation of the axis of symmetry. We'll then find the vertical intercept, and when we put in 0, right, vertical intercept is an x value of 0, we end up with just a c, so it's always the point 0, c. The horizontal or x-intercepts are found by solving our quadratic equation, quadratic formula, factoring, any of the steps or methods that we used before. And then we're going to plot all those points, and if we need more, we will. And I'm going to show you the technique of symmetric points, probably on a lot of these. So let's sketch the graph of the following. First thing I'm going to do is I'm going to write a equals 1.5, b equals -9, and c equals 7.5. Until you get used to just being able to look at a function and see a, b, and c, I encourage you to write these down. Okay, so we know that the graph opens up because a is positive. All right, so we're looking at a graph of this type. Next, we'll find the vertex. The vertex, we use the formula x equals negative b over 2a. In this case, that's a negative 9 over 2 times 1.5. So that's 9 over 3, which is 3. Now, first of all, this is going to be the x-coordinate of our vertex. We have to find y, but also this gives us an answer x equals 3 for our axis of symmetry. All right, and I'll explain a little bit more about that in a minute. So what's the y value of the vertex? Well, I'm going to put 3 back in my function. And check this out. This is really nice. When you're doing the vertex by hand, a really great way to check and make sure that you found it correctly. We're going to simplify this step by step. So that's 1.5 times 9 minus 27 plus 7.5. I don't want to add those yet. 1.5 times 9, I should know that. That's 9 plus 4.5. That's got to be 13.5. Now notice, we'll use our little yellow highlighter here. Notice that these two values, the one from the square and the one from the linear term with just the x, 13.5 is exactly half of 27. They have opposite signs. One's positive, one's negative. So when this happens, I know that my x value was correct for the vertex, and I'll show you that again in the coming examples. So when I add these two together, I'll get the sign of the larger one, the value of the smaller one. So it looks like that should be a -6. So we have our vertex, 3, -6. We have x equals 3 as our axis of symmetry. Our vertical intercept is the point 0, c. So I'm going to write that 0, c, which is 0, 7.5. And x-intercepts. Write the problem down correctly, and this will be easier, but I'm looking at this, and I'm thinking to myself, let me write this down first. Horizontal intercepts. 0 equals 1.5x squared minus 9x plus 7.5. I definitely don't want to factor that. Square root property won't work unless I do completing the square idea. And even the quadratic formula, I'm not really interested in. So I'm just going to call that eh. And I'll show you why. That's not always necessary. Let's graph this. What do we have so far? So on our graph, it looks like we have 3, 6, 7.5. So let's do 2, 4, 6, 8, and 10. I'm going to do that all the way around. If I just keep the scaling consistent, I really only have to write it one time. Let's see what we have. We have the point, and let's use green. Green, the point 3, negative 6. This is the vertex, and the parabola opens up, so I can label this vertex below. I have an axis of symmetry. I'm going to use maybe a light green to go through my axis of symmetry here. I'm going to do it correctly and not have those values because that was a miss. Yeah. I'm going to use x equals 3. That's a light green. X equals 3 goes right here, right through where x is 3. And it acts as a mirror, this axis of symmetry. It acts as a mirror. So check this out. When we have our vertical intercept in blue, 0, 7.5, so that's 2, 4, 6, 8, 7.5, we'll put right there. And I'm going to label it over here, 0, 7.5. What this axis of symmetry tells me is that, let's use purple. Purple's good. At the same distance away, notice how this is 3 units away. If I go 3 units on the other side, it'll be the exact same height. So I know I have the height of the y-intercept. Well, 3 units from 0 gets me to the vertical, 3 units from the vertical intercept gets me to the vertex. 3 units past that will be at 6, 7.5. I now have the width. I have everything I need. Even though I don't have the x-intercepts, which are probably pretty close to 2 and 4. Even though I don't have the x-intercepts, I can draw the graph of this parabola because I have the vertex where it changes direction. Nice little turning point. I have the y-intercept, which gives me something to tell me how the width looks on the left. And I have a symmetric point that gives me a width on the right. So my symmetric points will always be double the vertex x and use same c. So this will be 2 times the vertex coordinate for x, comma c is your symmetric point. Ooh, that sounded like the most complicated way I could explain it. Let's do it again. All right, so there's our first graph. I do have one normal one here, so we'll use that one normal one, and we'll actually solve it completely. Okay, so we're given f of x equals negative 0.25x squared minus 3x minus 15. A is negative 0.25, so I know the graph opens down. A value is negative, graph opens down. B equals negative 3, C equals negative 15. All right, so my graph opens down. My vertex, I know that x equals negative b over 2a. This is a negative 3 over 2 times a negative 0.25. You see a negative 1/4 times 2, that makes a negative 2/4. That's a half. So that's a negative 0.5. And if 3 is divided by a half, that is negative 6. The negative because the negative 0.05. 6 because 3 If I have 3 pieces and I divide each one in half, now I'll have 6 pieces. All right, we could find the y value. And you could use that trick I showed you. Or we could use our calculator, and I'm going to use that on this one. I'm going to put -6 and store it for x and hit enter. Now my calculator thinks anytime I type an x, it's -6. So I'm going to put -0.25 x squared minus 3x minus 15, and my calculator will give me the output. Turns out to be -6. You should definitely verify this. Verify this by hand. You should evaluate and make sure I'm right. All right, so here's our vertex. But also, we have the axis of symmetry, which is x equals -6. I know there's a whole bunch of 6's going on here, but that's all right. We'll work it out. Our vertical intercept, always the point 0, c. C is a -15. So let's see what we have here. We have a graph that opens down with a vertex at -6, -6. 1, let's call that 2, 4, 6 negatives. We're going to do even values here on the y scale as well. Okay, so we have an x value of -6, a y value of -6. We'll make it close enough as good enough. And because this graph opens down, I'm going to label this point above it. So here's my vertex, -6, -6. My vertical intercept, 0, -15. About right there. Now, we know this graph opens down, and we know it's about that wide right now. If you miss a point, make it bigger. It's all good. Close enough is good enough. Excuse me. But you see, we don't have any x-intercepts. This graph is never going to cross the x-axis. So if you use x-intercepts regularly to sketch your parabolas, you're going to have some where that's just not helpful. This other method, the method of the symmetric point. So symmetric to the vertical intercept, we will take the same y value as the vertical intercept, but we'll double the x value from our vertex. So over here at -12, I have to extend this. At -12, I will also have a height of 15. And this is definitely an issue of close enough is good enough in order to draw the graph. It's a little easier on our online homework systems, and it's easier if you have graphs on paper where you have some nice cross lines that you could do that. All right, so we can always graph a parabola if we have the vertex and the y-intercept, because we can always find a symmetric point to the y-intercept. We never actually have to have an x-intercept. All right, well, that doesn't look like it's going to fit there, so let's just move that down. Let's use a nice little blue here. All right, so my a equals 2, my b equals -12, and my c equals 5. A couple of things I can look at let's do this correct, just by looking at the equations. First of all, because this is positive, so my graph opens up. And the c value tells me my y-intercept is at 0,5. So those are things I can see immediately without doing any work at all. So I'm going to label this my y or vertical intercept. Next, I'll want to do some work on the vertex. The vertex has an x-coordinate equal to -b over 2a. It's -12 over 2 times 2. That's 12 over 4, which is 3. Remember to not just put this into the calculator like you see it. Simplify that denominator first, or else you'll get some weird answers using your calculator. Now, if I put in 3 for x, let's do this in our heads. You could check it on the calculator. You could write it out. But I know that 3 squared is 9. 9 times 2 is 18. I know 3 times 12 is 36. Notice 18 is half of 36. They have opposite signs. That's good news. So 18 minus 36 is negative 18. Plus 5 is a negative 13. Let me say that again. Negative 18 plus 5 is a negative 13. I really just said that one to make sure I was right. Once we have the vertex, we also have the axis of symmetry, the equation that is always x equals, and that what does it equal? It always equals the x-coordinate of the vertex. Now I could find, let me see, can we find our horizontal intercepts? Let's see if we could factor this. Let's go 2x times 5 and x times 1, so that's 10, which makes 11. That's not going to work. Let me see, if I do b squared minus 4ac using the quadratic formula, I will get 144 minus 4 times 2 times 5. So 144 minus 40. So we have a discriminant of 104. This tells me that there will be 2 x-intercepts, but it also tells me, since the square root of 104 is not an exact real number, it tells me that my x-intercepts will be decimals. Okay, I tried to factor, and it didn't work out for me. I used the discriminant. And I find that these are not exact integers. They are real numbers. They're just not exact integers. So that's not helpful. So when I graph what I have, 3, negative 13, our graph opens up. Let's see what we could do. 1, 2, 3. And I know I'm always going to double that x value from my vertex. So I'm going to go all the way out to 6. Let's make that 2, 4, 6, 8, 10, 12, 14. Make sure those are negatives. So we have 3, negative 13 as our vertex. I'm going to label it underneath. If the graph opens up, the vertex is a minimum, so I will label it underneath. I have 0, 5 as my y-intercept. And now to get my other point, I know I'm going to double my x value from my vertex and get 6. Keep the same y value as my y-intercept. And see what I can do to sketch this graph as best as possible. You can see I got a little crazy here. I could probably bring that in closer. Let's see. I forgot it was going to erase so much. There we go. Close enough is good enough. You know, these graphs, when we're sketching them with no lines, nothing, we're getting the basic idea. If you're using an online homework system, there's a couple of different ways to graph them. It depends on your homework system, so please let your instructor know if you're having problems with these. All right, so let's not forget, I have this fancy tool right next to me, this graphing calculator. What happens, and anytime you're graphing here, what happens if we graph this on our calculator? Can we put the values here in for what we need to graph? Keep in mind that even though I said x is the value negative 6 earlier, when you're graphing, it'll use the generic. It won't replace specific values at this window. On a regular negative 10 to 10 window, we see a vertex. We see that this graph opens down. We knew it would because the 0.5 is negative. Let's find our vertex. Let's find our y-intercept. And notice there are no x-intercepts. This is why I frequently do not even worry about x-intercepts. All right, so let's go with blue and just write down everything we know. A equals a negative 0.5. So the graph opens upward. And I'm using my mysterious magic disappearing ink. That should come back for us. I just don't know when it will do so. All right, let's see. We know our vertex is at, no, let's not do that. We know our y-intercept. All right, I've tried to make my disappearing ink come back and it won't. So let's see what we can do here. All right, so for our vertex, we use x equals negative b over 2a. That's a negative 4 over 2 times a negative 0.5. 2 times a half is 1, but because that half is negative, that'll be a negative 1. We get a 4. Y value. Put the 4 in for x. Check this out. If you go to the table, see how in our table at 4, right, an x value of 4, the y value is negative 2. Also, as we're looking at this, the negative 2 looks like it's the highest y value. And then on either side of it, we can see that on either side of the negative 2, we can see that the values are the same. All right, we have negative 2, and then on each side negative 2.5, and then negative 4s, and then negative 6.5. So we can see this 0.4 comma 2. Let me grab my pen back again. As our vertex, and we can verify it on a table of values that indeed will be our point, a turning point. We have the axis of symmetry, which is x equals 4. My disappearing ink doesn't look like it's coming back. I don't know. Oh, I'm getting flashes. Maybe it will. I'm going to write it again just in case. My y-intercept is the 0.0 comma negative 10. Remember, this graph opened down. It doesn't have any x-intercepts. So a nice symmetric point, double the x value of the vertex, use the y value from the y-intercept. So we have, let's see, everything's going to be down below. So let's use 2, 4, 6, 8. And 2, 4, 6, 8, negative 10. We'll have this point here at 4, negative 2 as the vertex. We'll have 0, negative 10 as our y-intercept, and we'll have the point 8, negative 10 as a symmetric point. And now we can graph it. Let's pretend you don't have that little bubble in your line there. All right, what happens? I think I take off too much of it if I try to erase it here. Okay, close enough is good enough. But I do like those arrows on the ends. All right, I don't know why my disappearing ink still hasn't come back, but I wrote down most of the important stuff there. The a value was negative, so my graph opens down as we verified. We can find the vertex, we can find the axis of symmetry, we can find the y-intercept. The hardest work we do is finding the y-coordinate for the vertex because that's where we have to evaluate a function. Otherwise, that's it for graphing quadratics from standard form. Thanks for listening.